new space, our new classroom, room 1160. No more room 5. This is the new room 5. So I'm glad people have arranged themselves what I think is a reasonable way in this space. I think the perspective will be very hard. I plan to just use the front boards. Maybe occasionally we'll need some extra space. We can use that, but I won't use the space behind us and to your right. Okay? Right, okay. So, let's see. Firstly, our announcements. So, there is a problem set 7 that is available if you haven't already looked at the assignment. It's a fully extra credit assignment in terms of some exercises thinking about quantum field theory for electromagnetism. Okay. I'm not sure yet where we're going to hold office hours, but we'll just get started at my office and we'll see. We'll find there's a ton of space everywhere. We'll just decide where we want to be. I haven't yet decided. Okay, but I will hold my office hours as usual today at 3 o'clock in my office, which is the Fishbowl, room 2000. Okay. I'm purely glass. It's pure glass. You can watch and see when I'm surfing the web. Right. So, what remains for the semester are 3 more homework assignments, some of which will be some extra credit assignments. Oh, you're not allowed to bring your bikes in here. I'll remind you for the future. So, we'll have 3 more problem sets, and then we have our final project, which will be due during finals week. Okay? And so, I will be discussing that more very soon with you, what the plan is for that. The basic plan, the basic assignment is that everyone will be responsible for writing a Wikipedia page on some topic in quantum optics of interest to you. The purpose of this assignment is multifold. Number 1 is so that you have an opportunity to research a subject of interest to you in quantum optics and write about it. But there's another reason, another lesson to be learned, I hope, from the assignment is what is actually on Wikipedia, and is it good? I mean, people use Wikipedia as if it's, you know, the stone tablets come from the burning bush. I think there are lots of, it's gotten better. I used to have real tirades against Wikipedia as, you know, who is writing Wikipedia? It's a good question. Who is writing Wikipedia? Well, maybe you guys should be writing Wikipedia. Has anyone ever edited a Wikipedia page? Yeah, okay, more than at least a couple of people. But, you know, we should be editing Wikipedia. We are the source of knowledge. Who is? That's what we'll be doing, and the homework will end soon enough for you to get started on that. All right? Very good. All right, so last time we were talking about, in our makeup lecture, the way in which, I'm playing around with this stuff. Interesting. This is interesting. I can't really run it. This is really dynamic. We'll figure it out. So, what we were talking about last time is the way in which we should think about a quantum field theory as a theory of both particles and waves, as we know from quantum mechanics fundamentally at its foundation is about wave-particle duality. And quantum field theory is a kind of formalism that encompasses both the wave nature and the particle nature. And as we'll see, it allows us to relate ultimately the waves that we think about as probability amplitudes to the waves that we think about as classical waves when that's appropriate. So, for example, electromagnetic waves or sound waves are classical waves, but there's also a quantized theory of those waves, and we're ultimately going to, sort of the grand finale of the course will be to understand the way in which we can think about classical electromagnetic waves as arising from the fundamental underlying quantum field theory of electromagnetism. Okay. So we think about our quantum field as having different kinds of degrees of freedom. We can think about them as having wave degrees of freedoms, where we think about oscillators, which have things like observables like the quadratures. Those are sort of wave properties of the field, sometimes known as continuous variable degrees of freedom, because as we know, the position, or x and p quadratures have continuous spectra. Or particle degrees of freedom, where the quanta of excitation of our fields are the particles, the fundamental particles, or quasi-particles, if it's something like a phonon. And we have this duality. We can think about the mode functions that we use to discretize our field theory as the wave functions of the particles. So if we were to create a particle in a single normal mode, we would say that the wave function associated with that phonon is that energy eigenstate, and that's its wave function. Okay? So there's these interrelations that we have to think about a little bit more and learn about a little more. The Hilbert space that is the space upon which the field operators act is Fock space, and we think about that as the tensor product of Hilbert spaces for each of the modes, which represents a degree of freedom. And the basis, the standard basis for that Hilbert space we call the Fock states, which are the states in which we have some number of quanta in the given modes. Okay? So that forms a basis for the whole Hilbert space, for the whole quantum field. Okay? And we can obtain these states by creating, so now what was the raising lowering operator for the harmonic oscillator now becomes a creation operator that creates a particle in that mode. Okay? So this, we want to create n particles in the kth mode, we apply the creation operator k times and normalize appropriately. Okay. And one of the other interesting things we saw last lecture was that the many-body nature, so it's an important point, there's an intimate relationship here between quantum field theory and many-body physics. So, we talk often about field theorists, we're often talking about people who are working in either condensed matter and or high energy, because there's an intimate relationship between quantum fields and many-body physics. And when we want to think about a description of having multiple particles when they are identical particles, so this is should be full state, we have two different ways of looking at it. We can think about it as we just discussed. I can create, say, one phonon in the mode K1 and another phonon in the mode K2. That's this kind of second quantization picture of this two-particle state. And as we showed, we can look at the sort of effective two-phonon wave function of that state, and it's already taken into account due to the fact that these different creation operators, I'm going to have ink on me for the rest of my life in this room, commute, that the two-particle wave function is symmetrized. I can't say which is particle 1 and which is particle 2. Particle 1 could be in mode K1 and particle 2 in mode K2, or the other way around. And I have to have this positive sign, which is taken into account through this. And that was appropriate because this was a theory of bosons. And this was a theory of bosons because our phonons were spin zero. They were, it's a one-component field theory and thus a spin zero theory. Okay. Yes, sir?
Sorry, can you just remind me what you mean by minus first quantization?
Oh no, that's not a minus. That's just meant to be a dash. I'm saying there's two descriptions of our two bodies. This is what we would call the first quantization, where we just think of a theory of wave functions. And as we described last lecture, what's called second quantization is where we kind of quantize the wave function. It's a stupid term, really, but it's a term that we still use. Really, there's just two different formulations. One in terms of explicitly just restricting the set of functions to be the ones that are symmetric under exchange. And another is writing it in this formulation in terms of Fock space. This automatically takes into account the symmetrization, whereas this you'd have to do it by hand. And just say that there's a selection rule of sorts, a superselection that says we can't have states other than the ones that are symmetric under exchange of the two particles. Great. All right. I'm also going to lose the cap. Anyway, my pocket, my spoon. Yeah. That's very fine. All right. Let's let that pen dry out, and let's go over here. Right. Okay. So, what we were talking about as well, and we're going to continue on now, is thinking about the electromagnetic field. Oh, I see. Excuse me. I knew I didn't annihilate. All right, the electromagnetic field, electric and magnetic. This is, as we discussed, this looks like a 6-component field theory, but that of course is not true because E and B are connected to one another through Maxwell's equations. And if we think about the free field, this is to say the field without the charges and charge density, then we have Maxwell's equations written as such in Gaussian units. And these constraints mean that, in fact, what is, we can specify the field by, instead of the electromagnetic fields, by the potential, the Ford potential, which has a scalar potential and the vector potential, right? This is a 4-component field. And the magnetic field, of course, is the curl of A, and the electric field is this. Okay. And as we discussed at the end of the last lecture, what this equation tells us, if we put these two equations together, this tells me that del squared phi, so del dot E equals 0, implies that del squared phi is equal to minus 1 over c d by dt of the divergence of A. And because of that, what this says is that phi is not an independent dynamical variable. If I specify on at initial time what the vector potential is, then that specifies what this is at all later times. Because I can just write, this is a Poisson-like equation, and I can write the solution. So that means that phi is not an independent item. And we can just eliminate it. And so we're left now with the 3-component field. Okay? So in terms of the quantization of the field, where we have is 3 components specified by the vector potential. And these 3 components means that the photon is spin 1. Because there are 3 components. You have 2s plus 1 components. S is therefore 1. Okay? Now, as we, of course, also know, importantly, we have gauge freedom, which is to say that if I make a transformation whereby I add to the vector potential any gradient of any other scalar, I do not change the E and B, right? And thus, what that says is I can change the divergence of A in any way I like. I can choose it to be anything I want, and I won't change the theory. The curl of A matters. The curl of A determines B and affects E. But the divergence of A, I can shift, because if I look at the divergence of A, that's related to the divergence of A depends on then plus the Laplacian of chi, and I can make the Laplacian of chi anything I want. I can change the divergence of A in any way I like. So fixing the gauge is equivalent to fixing the divergence of A. Okay? And as I described, to remind you, any vector field can be broken up into what's called a transverse field and a longitudinal field. The transverse field has 0 divergence, and the longitudinal field has 0 curl. That's known as Helmholtz theorem. And so the longitudinal part of A, the part that doesn't have a 0 divergence, is irrelevant. I can change, this is equivalent to saying that this is arbitrary. I can choose that any way I like without affecting the electromagnetic theory. Okay? Because that's the part that has, in general, some divergence. But I can choose that any way I like. So, there's lots of choices, but the standard choice in quantum optics is known as the Coulomb gauge. And we just set the divergence of A to be 0. We could use anything we want. Why not choose that? And let's keep it around. Okay? So in this case, that means that A is a purely transverse field. The longitudinal part is 0. Of course, what that also means is the scalar potential is 0 in this gauge for a free field. Now, I remind you, you should have learned in 511, if you've taken 511, that in the Coulomb gauge, when you have not the free field, but if rho is not 0, you have charge in the problem, then the scalar potential is just a function of the charge density. So it's really another way of just expressing the charge density. That's why it's a degree of freedom that really is a charge degree of freedom, not a field degree of freedom. Okay. So we work in the Coulomb gauge in quantum optics. It's not the standard choice in relativistic quantum field theory, because the Coulomb gauge is not Lorentz invariant. If I go to a different reference frame, I have to change the gauge. So in field theory, in relativistic field theory, we typically work in the Lorentz gauge, right? You remember that from your E&M. But that's, quantizing in the Lorentz gauge is a total mess and is not important for what we're doing. So we will just do the simpler thing and stick with the Coulomb gauge. And in the Coulomb gauge, the electric field is this, which itself is just has the transverse part. So in the Coulomb gauge, del dot E is 0, as we want it to be. And the longitudinal part is not quantized. B, of course, always is purely transverse. It has no longitudinal part ever because there are no magnetic monopoles. I'm sorry, parallel. Okay, so we only quantize the transverse part of the field. All right. So to quantize this, the first thing we want to do is think about we could go through the Lagrangian and all that, but we don't need to do that. All we need to do is ask ourselves, what are the normal modes of the problem for this electromagnetic field? What is the nature of the normal modes? And then to each normal mode, we assign a harmonic oscillator at the end. Yes, sir?
Why is E parallel not quantum?
Well, that's what this whole thing was about. So what I was saying is that the parallel part of E is just related to, if I look at that, it depends only on, if I look at the divergence of E, it depends on phi and the part of A that has a divergence. The longitudinal part of E, so if I break this up, the longitudinal part of E is this. Let me do this. Is that clear why that's true? Because the transverse part of E,
Yeah, that's clear.
okay,
A
and
parallel
is 0.
Parallel is made of photons.
It is not. It is not. A parallel is it's just a relation. There is an intimate relationship. Phi and A parallel are one and the same. And from what I was describing up here somewhere. Yeah. So this is aparallel. And so aparallel is not an independent degree of freedom. It's really, aparallel encodes information about the charges, not the fields. Yeah?
Aren't the charges quantized though?
They are, but it's not, I mean, it's not quantized in terms of the, what I mean to say, it's not a quantized degree of freedom of the field. It's really a charged degree of freedom. So we're talking about the quantization of the field degree of freedom, not the charges. Separately. All right, so with that said, we need to write down what the equation of motion of our vector potential is. So we have Maxwell's equations up there. Let's look at, we have, for example, B is the curl of A. And here A, when I write A, well, I'll emphasize here, it's only the transverse part of A that we quantize for the field. So, if I take the curl of this again, as we love to do to derive the equations of motion, and use our favorite identity for the curl of the curl, right? This is equal to 0. And the curl of B is equal to minus 1 over C dE dt. But E is equal to minus 1 over C dA dt, so that is equal to 1 over C squared dA squared dt squared. And so we have as expected the vector potential satisfies the wave equation in 3D with our gauge choice that is transverse. So this is the wave equation in 3D for transverse waves of the free field. All right, so now the question is, how are we going to decompose that into normal modes? I'm listening. Well, I'm trying my best to try and erase this thing. So I want to decompose my vector potential into normal modes. What are the normal modes of the theory? Well, I have, this is the equation of motion here, right? I have the wave equation. I'll write it again. So the normal modes, well, the normal modes, they are going to be some kind of vector that depends on position, and then they should oscillate with some frequency. Those are the normal modes, right? As we discussed using the separation of variables. So if I plug that in, the normal modes, which I'll write. So I'll call this omega sub k. And now my modes depend on that k so far. So now, what are the solutions? This, of course, is another thing called Helmholtz equation, not Helmholtz theorem. So any set of modes that satisfy Helmholtz equation are good, depending on the boundary conditions, right? So we have to decide on the boundary conditions if we want to think about a discrete set of normal modes. Otherwise, we have an uncountably infinite set. Makes life's a little more complicated. I could use spherical waves. Spherical vector harmonics, chapter 16 in Jackson. Those are perfectly good set of modes, but you know, we generally wouldn't do that unless we were forced to. What's the standard set of solutions to this? Plane waves, right? So we would look at our plane waves as the normal mode functions, okay? Now, typically what we do is we create what we call a quantization volume. This is just a fictitious volume which allows us to put boundary conditions on the system with some length along each of these guys. In which case, my normal modes, if I think about, as we would typically do, think about periodic boundary conditions. So that our modes are traveling wave modes rather than standing wave modes. Now, just as an aside, as we will get to maybe today, if not Wednesday, sometimes this is a real, honest-to-God volume. I might have, you know, a microwave cavity that looks like that, and I have, you know, reflecting walls. Or I might have a Fabry-Perot cavity for optics, which has mirrors, in which case the boundary conditions would be the hard wall boundary conditions. But in free space, what we typically do is we put a fictitious volume at the edges of the universe with periodic boundary conditions under the hope that we never get to the edge of the universe. And if we ever do, we take the limit. If we want to look at the truth theory, we ultimately take the limit as the volume goes to infinity. Okay? So, with that said, what are my normal modes? Well, now I write them in terms of, remember we had 1 over the square root of length times e to the I k x, and we had the 1D periodic boundary condition. But now I have e to the I k x with a certain component of the wave vector along x, y, and z. So I can think about this in the following way. Those are my three I've separated coordinates along x, y, and z, or e to the 1 over the square root of the volume e to the I k dot x, where periodic boundary conditions for the alpha component, this is some multiple of 2 over the length along that alpha is x, y, or z. And j is plus minus 1, plus minus 2, etc. So those are my normal modes. They're now specified. Oh, wait a minute. This is a vector. And these are scalar functions. So somehow I need a polarization here. Right? And that polarization vector, we'll come back to it. Well, this, of course, these modes are now specified by these 3 numbers for each j, right? What about this polarization? What about it? Well, we have to satisfy this, right? So that means the divergence of this has to be 0. Which of course implies that the polarization vector must be transverse to the direction of propagation, the wave vector. So if I think about a wave vector here, the wave vector has a magnitude omega over c and some direction. I'll call that direction little e is the unit vector. I don't like to put hats on my unit vectors because hats are for operators. That's the direction of k. Okay? And then in the plane, my polarization sits in the plane perpendicular to the, hence the plane wave, right? Now, there are a basis, I can have 2 different orthogonal vectors that span that space. And we typically, so my polarization vector now depends on what plane I'm in. So it depends on k. And then I have 2 different polarization vectors. For example, I can have linear polarization. I can have say, horizontal polarization. Well, that's vertical. And horizontal polarization, where EH cross EV is EK. Of course, these depend on K, right? Because if I have a different K, I have a different horizontal direction and a different vertical direction. So it's somewhat traditional to label the index of which polarization it is by lambda, even though lambda is the wavelength. Often when you redefine it, we define them as lambda. 2 different polarization states where lambda could be H or V, for example. All right. Now, it's another basis which is very useful for us to think about in terms of different polarization states are the states with circular polarization. Okay? So we define, if this is the k vector, if the polarization is rotating with the right-hand rule and you're writing, make sure you put your pen down, as E plus, that's EH plus I EV over root 2. So this is epsilon k lambda equals plus 1. Or the other way around. If the polarization is rotating like that, that's EK minus 1, which is VH minus I. And often we like to work in that basis. Either one is a good set of modes. Okay? So, given that, we can decompose our transverse vector potential in terms of these plane wave modes in the quantization volume with periodic boundary conditions. Yet, you know, I don't know if you guys heard, but the faculty voted in favor of a union. I'm going to go on strike if I don't get a blackboard.
That one did get recorded. Just letting you know, like.
I don't know
Edited
if
it out,
my
right?
Apple Watch counts my calories on this thing. Sure. Anyway. All right. So, firstly, these modes are orthonormal. So, if I integrate over the quantization volume, let's see what I get. So this is the integral over the quantization volume. 1 over V epsilon star K. Actually, is take the epsilons, the polarization vectors outside the integral. Right? Everyone agree with that? Okay. What is this? Well, let me put the V in here. So what is this? That's a Kronecker, right? So this is a Kronecker delta K, K prime. That really is just a shorthand for all three components have to be equal, right? And therefore, I get which is equal to what? Oops. Yeah.
So it's function for lambda.
Right. So the two polarization states are orthogonal. If I have the same K, this and this are orthogonal based on the star, the complex dot product, right? If they were horizontal and vertical, it would also be true, right? Of course, it has to have the same K. If they don't have the same K, then I can't say whether or not they are orthogonal or not. So this is equal to delta polarization, delta if I sum over all the plane wave modes and all polarization states, and I look at the ith component of this guy and the jth component of this guy, the question is this a complete set of modes? If it was complete, I would have this function. Right? That's the completeness relation. That if we didn't have the vector part, as we discussed last time, a complete set of functions that spans the Hilbert space, this would be a delta function, right? Now, it's kind of tricky. This isn't actually true. Why aren't these actually a complete set of vector fields for all possible vector fields in the quantization volume? Why is this? Why? Yeah.
You've lost any component frequency lower than
it's not about the frequency. I can go all the way to DC here. If I have periodic boundary conditions, I can make a flat function here. But you're onto something. There's something that's not, this doesn't capture. And these functions don't capture all possible kinds of vector functions in 3 fields. What am I missing? The longitudinal part. These functions are transverse. These functions had a constraint that this was true. So this is we would have to put like kind of a T on here. This is what's known as the transverse delta function. It's a complicated bit. It's not really that important for our purposes, but I'll just mention it. That it's very subtle points when you're thinking about completeness relations, you have to remind yourself that you're only dealing with the part of the vector field that has 0 divergence. There's another part of the vector field that has a non-zero divergence, and that's not part of this quantum field. All right, with that said, now we can write down the decomposition of the vector potential and thus the electric and magnetic field in terms of these guys. I'm going to leave this guy here.
Ivan.
Ivan,
I'm listening.
why is the Kronecker the one that's transverse?
Yeah, actually, you're right. That's a stupid way of writing it. This whole thing should have a transverse on it. It's really what this is the following. So if I had a delta function in 3D, I would write it like this, right? This is a scalar delta function in 3D, integrated over all k. You agree with that? This would be a delta function. But what I have in this is the following. That's the transverse delta function. If I didn't have this thing, this would be a delta function, and this would be a Kronecker. But I have to take, if I look at the divergence of this, it's going to take out the part that has any component along k. This complicated object there is the transverse delta function dyadic. It's ij component. That's what the thing really is, if I cared. So without this piece, this would be a delta function. And then I would have just the delta ij. But this subtracts off the piece that's along k. All right, good. I have no idea what time it is. Oh yeah, it's that time. We have 20 minutes plus whatever I get later. All right, so let's see. Let's write down now the vector potential. I'm now quantizing it. Da, 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 da. It has a hat on it. This is the free field potential. I have a sum over all the modes, which are labeled by their wave vector and their polarization state. I have some, I'm going to leave a space for the characteristic units. I have for every mode, I have a and A dagger. Actually, here's what I'm going to do. Let me write this down and I'll explain what I'm saying here. Sorry. All right, I promise this is what I want. So let me explain what I've written down here. I've decomposed, as we did for the phonon field, my field in terms of normal modes. The normal mode expansion coefficients, once we've written it, are now what was the probability amplitude now becomes A, the annihilation operator, which in this case annihilates a photon in the plane wave mode K with polarization lambda. This is in the Heisenberg picture. In the Heisenberg picture, the operators are functions of time. Now, there's a characteristic scale here of the vector potential for that mode. That's what that script A is. I factored out, remember this thing has units of 1 over the square root of volume. So to make this thing have the same units of that, I've put that there. Okay. if I express this out, write in for the case of the plane wave modes, then this is equal to the sum over k and lambda, this characteristic scale. I'll put in the free field time dependence. Plus the Hermitian conjugate, which I'll write out for fun. Voila! That is the quantized vector potential for transverse wedge. Oh, we forgot one thing, the polarization. So I create a particle, a photon in this case with that mode function. And then I have on this side everyone clear on that? Questions about that? Yes, sir.
So now you've absorbed your root V.
Yeah, so it's gone, right? There was a one over root B that canceled this guy. What is the electric field? Which is just the transverse part. Well, that for the flip gets this. Which is equal to characteristic electric field scale is just K times that of the, because I brought down an omega over C when I took the time derivative here. HC stands for Hermitian conjugate. And the magnetic field is this. Notice that the characteristic scale of the magnetic field is exactly the same as the characteristic scale of the electric field, because the electric field and the magnetic field have the same units in conjugates, right? And that comes down, what I did is this originally was K cross epsilon, and then I factored out the magnitude of K, and it gave me the same thing that we had before. All right? Hooray! We have the quantized electromagnetic field. Yes, sir?
How do you determine what are the AC phase?
Exactly. So that's the thing that's missing. What are these characteristic units? So we have to decide. That's the last thing we need to do to fully define this thing. All right. Let's do it. So, to define that, we have to think, what are the characteristic scales in the problem? Well, what we want to be true is that the energy in the electromagnetic field is the Hamiltonian of our field theory. So to fix the characteristic unit, we have to fix the characteristic energy. And then we're done. All right. So, the Hamiltonian for the free field H. Well, that's the energy in the electromagnetic field. What is the energy in the electromagnetic field? E squared plus B squared with some units, right? So this is equal to the integral over all space. That's our quantization volume. E squared plus B squared. And in these units, it's over 8 pi. Otherwise, it'd be epsilon naught over 2 and then 1 over 2 mu naught, if you were so inclined. I'm bilingual. All right, so what we want this to be equal to is the Hamiltonian for our field theory, which each mode is a simple harmonic oscillator. And so this is supposed to equal the sum over all the modes, which are denoted by a wave vector and a polarization. And then we have h bar omega sub k plus a half times a dagger for that mode. Is that clear? Every mode is a harmonic oscillator. And this is the Hamiltonian of the harmonic oscillator for that mode. N plus half, no, what? That's not clear at all. What's wrong? What am I thinking? N plus a half times h bar omega. Omega sub k. Notice that omega doesn't depend on the polarization, it just depends on the magnitude of k. Right? So, by that constraint, we can now find the characteristic scale. Okay, let's do it. So let's look at the integral over the quantization volume of this. Before I do that, I want to just make a notation over here. The breaking, notice all of our quantum field has the terms that depend on the A's and the terms that depend on the A daggers, right? The Hermitian conjugates of one another. The terms that go like A for the free field go like e to the minus I omega t, and the other ones go as e to the plus I omega t. We remember that the e to the minus I omega t was the right convention for going around clockwise. And that's a positive frequency. So this term is called the positive frequency component of the field. And this term is called the negative frequency component. same for E and A. That decomposition into the positive and negative components is going to be extremely important moving forward. So this is equal to the integral, I'll just write out. Oh, by the way, this thing, of course, is just a Hermitian conjugate of the positive frequency component. Right? So take the conjugate. That's why we went Hermitian conjugate. Right? So this is equal to this plus HC plus so those are the four terms. Writing this as E plus plus E minus, and this is E plus plus E minus. I have four terms. The pluses with the minuses, and the pluses with each other, right? And those are the four terms. So I have to calculate this, and then I have to take the Hermitian conjugate of each of those terms. All right? So let's do that. I'm too lazy to erase another full board, so I'm going to use this guy. Bad professor. All right. So let's look at this. And we're going to plug in this. All right? So I'm going to take the sums outside the integral. I have the sum over k and k prime, a sum over lambda and lambda prime. I have epsilon k star dotted into epsilon k prime lambda prime. I have E, C, K, and E, C, K prime. And then I have A dagger K lambda, A K prime lambda prime, and then an integral over space e to the I k minus k prime dot x. Do you agree? Once I wrote in E minus and E plus and integrated over the all space. All right? So now the question is, what is this? It's a Kronecker delta times the volume, times the quantization volume. Because when it was 1 over V, it was a Kronecker delta, right? Okay, so now I can do the sum over the k primes. And the k equals k prime. And I have that times v. Right? What is this? That's a delta function in the lambdas. So what I get here is the sum over k and lambda k c squared a dagger a. I have that plus its Hermitian conjugate. That's this. Finally, we have to do this guy.
You still have,
there was still a sum over k here, and it's no lambda prime. Yes, sir.
We're assuming the curly E is real.
No. Oh, this guy? Yeah. That's our characteristic scale. Yeah. I thought you meant these guys are not necessarily, but this is just a number. We don't have to, but it wouldn't. You know, it basically is a phase convention for the overall mode. We'll come back to that in a moment. All right, let's do this. So now I'm going to cheat. So now there's no star here. They're both E minuses, and they're both like that, right? Because they're the same. I'm looking at this term over here. There's no stars on anything, and no daggers on anything. So what is this now? Well, now I got a minus sign there. So now I'm going to have that. There's no star here. So now, what am I going to do? Well, we'll restrict ourselves just because the calculation is easier. We can choose any basis I want. I will use the circular polarization. Yes?
CK square because CK and CK minus C minus K.
This only depends on the magnitude of K, not the direction. So we don't care. So for circular polarization, if I have E with a certain K and lambda, and I look at what that is with minus, what can you say about that? I mean, with minus K. It's going the other way, right? So this is, which is of course just a complex conjugate of that. So this vector is the one going in this direction, E of minus lambda, and that is the conjugate. So I can write this as this, which gives me a delta lambda lambda prime on that. So this term is this. All right, let's put it together. What we have is that the integral over the volume of the electric field squared is equal to the sum over the modes, the characteristic scale squared, AK dagger AK plus AK dagger. That will come from the other term that we didn't put in. And then we have plus, there's a tiny thing here. This dependent. I have this times this. out about that I. So there's an I squared here. It's this minus, minus, minus. That's the electric field part. Now, we don't have enough time, but I will leave it to you to show that the following thing is true. It's in the notes, you can go through it yourself. I have exactly the same thing, except these guys become positive signs. So I have this term, I have that term, I have that term, I have that term, I have that term. But where there's a minus sign here, there's a plus sign there. That comes from the different direction of the magnetic field relative to the electric field. E cross B is in the direction of K. And so when I add these two together, my Hamiltonian is equal to the following. Sum over the modes, V ek squared over 8 pi, or over 4 pi, because I have this plus this, A k plus A dagger. I add these together, divide by 8 pi. I have these two are the same, and these guys cancel. Which is, of course, equal to the sum over k and lambda v over 2 pi e squared n plus a half, where n is the number operator. So now I ask you, what is the characteristic scale of the electric field associated with a given mode?
Like square roots with omega.
Yeah. So this is supposed to equal, we have it somewhere, maybe not anymore, sum over the modes n plus a half. And so what we have is that the characteristic scale of the electric field is equal to the square root of 2 pi h bar omega over v. And with that, we have the full description of the quantized electric and magnetic fields. Now, I just want to conclude with one statement. Could we have guessed this? Well, we could have gotten damn close, because we know that energy density is E squared. And if I have a photon inside a volume of volume V, its energy density is h bar omega over V. So the electric field is the square root of the energy density. It's the square root of h bar omega over V. Now this factor of 2 pi, that's, that's a matter of what units you have. It might be you know, a 1 over epsilon naught times something or other, if you were so informed. But that gets all the factors right in the end. We have to have it there. But we could have guessed this if we want, and we should have guessed that. Excellent. All right, so we have quantized the field, and now what we'll go on to is try to examine a little bit more the properties of this quantized field, and then begin our discussion of the interaction of matter with the field when the quantum fluctuations are important. Pick that up on Wednesday. Have a good afternoon, everybody.